Mario. So we will start the last lecture in this morning session, and the last speaker is Marco Gualtieri from the University of Toronto, and the title of his talk is Generalized Kahler metrics as Lagrangian branes in double symplectic groupoids. Marco.
All right, thank you very much. And thank you to the organizers for organizing this great event. It's been a real pleasure to be here. So I'm going to give an update and kind of hopeful conclusion to a project that has taken many years to develop. It kind of began with work that I did in my thesis under Nigel Hitchin. And after finishing my thesis, I went immediately to visit Alan Weinstein, who started to try to explain to me the importance of symplectic groupoids. And my eyes glazed over at that time. And then after becoming friends with Enrique Burstein, he also explained the primary importance of symplectic groupoids, and my other eye glazed over at that point. And so, of course, when those things happen, it should not be a surprise that 10 years later or 20 years later, you end up speaking about double symplectic groupoids. So now I give back the favor and create pain on their side, hopefully. So this is what I will speak about, is the kind of amazing appearance of symplectic groupoids and double symplectic groupoids in the topic of generalized Kahler geometry, which really has its origins in physics and in the study of two-dimensional supersymmetric sigma models. So the plan is, I'm going to just explain basically what a generalized Kahler structure is, and then we'll immediately go and extract all of the holomorphic data that a generalized Kahler structure contains. That's what I mean by holomorphic reduction. And then after that, I'm going to explain how to integrate a generalized Kahler structure. That's really the whole purpose of this talk, is to explain something about the inherent structure of generalized Kahler that includes this question of integration. And I'm first going to do a simple case, which is called the symplectic type case, which I've spoken about many times in the past few years. And then after the halfway point, I'm going to explain somehow how you generalize this to the general case. And I'm going to use several tools in order to do this. One of the important tools is a method developed by Pavel Cevera, which greatly generalizes the work done by Attia and Bott and by Alexeyev, Malkin, and Meinrinken on the moduli space of flat connections. He really had, in my opinion, he's a visionary in this area, and he really contributed a lot to the way I think about the topic. The other thing that's going to occur is these double structures, which I learned about from Kirill Mackenzie. And at that time, it wasn't my eyes that were rolling over. I was just on the ground. I was just dead with the double structures. And so anyway, now those make a resurgence. And then something which is quite interesting, which I call the Burstein shuffle, and I hope you don't object. We'll see what that is, and that's a main tool in explaining these double structures. Okay, so what is a generalized Kahler structure? Very simple. We have a C-infinity manifold, and we have a closed three-form on it. That closed three-form is the Neveu-Schwarz background three-form flux, or you could think of it as the curvature of a gerb, but it's just a closed real three-form. And from that information, you can produce this Courant algebroid, T plus T star. It has a natural orthogonal structure, split signature, and it also has this bracket, which includes the three-form, the Courant bracket. So on this background, what do? You choose a pair of complex structures. Complex structures on complex structures on this bundle. These are called generalized complex structures. And we want them to commute. I call them JA and JB because of the fact that the standard example is that of a symplectic structure and a complex structure. They both can be thought of as complex structures on this bundle. And if they are Kähler, if this pair of information is Kähler, meaning that the complex structure makes omega of type 1,1, or in other words, that we obtain a Riemannian metric from their composite, then we call this a Kähler structure, and this gives an example of a generalized Kähler structure. These two matrices commute. So that's all that it is. It's a generalization of Kähler geometry. Okay, and when you study this structure, the first thing to notice is that because of the fact that JA and JB commute, that means that the eigenvalues of JA break up into the eigenvalues of JB. And so that means that if JA has plus I and minus I eigenbundles, which I just think of as vertical lines here, then those eigenspaces decompose into the plus I and minus I eigenspaces for JB. And so what that means is that we have 4 eigenspaces, eigenbundles. Okay, and I've drawn them here in red and blue, and I've called them little l plus, little l minus, and their complex conjugates. So T plus T star splits into a sum of 4 things, which I would call them half Dirac structures, because the sum of any 2 vertical ones or horizontal ones, those are plus I eigenbundles of this generalized complex structure. This generalized complex structure is compatible with the split signature orthogonal structure, and so it means that this red space and this green space are both Lagrangian, maximal isotropic. Okay, so we have 4 maximal isotropic big Dirac structures, and then we have these half Dirac structures, which are their pairwise intersections. But it's important that the diagonal pairs, if you take L plus and L plus bar, right? So if you take the sum of these two, this will not be a Dirac structure. In fact, it's positive definite, and the one with negative sign is negative definite in the split signature pairing. And so what happens is that you get a subbundle, which is the graph of a 2-tensor made of a symmetric and a skew-symmetric part, so that way you can extract a Riemannian metric and a skew 2 form. Okay, so L plus L plus bar turns out to be defining us a metric, a usual metric, a traditional metric. Okay, and because this is positive definite, whereas T and T star are null, that means that the projection from the blue space down to T is an isomorphism, and the decomposition of the blue space into L plus bar and L plus, that will induce a decomposition of T, and therefore a complex structure on T, a complex structure on the manifold. So what we end up with is one complex structure on the manifold, a usual complex structure coming from this decomposition, the positive decomposition, and we get another complex structure, I minus, coming from the other decomposition. We have 2 different complex structures on the same manifold. So, and both of these complex structures are compatible with the metric. And so this is called a bi-Hermitian structure with 3-form flux. And the important thing is that these are not Kähler. So it was discovered, this geometry was discovered by Gates, Hull, and Rocek in 1984. They obtained the bi-Hermitian formulation, and they realized that the requirements of supersymmetry for this 2-dimensional sigma model with target in this Riemannian manifold would require not that omega plus and omega minus are closed, but instead that their DC cancel each other out and equal this closed 3 form. So you can see from this equation that DC omega plus and DC omega minus are not zero, but they are closed. And so you could phrase it in a different way. You could say that DDC of omega plus is zero. But in any case, this was a very confusing type of geometry at that time. Mathematicians were not really able to analyze it. But with the advent of generalized geometry, it became possible to really make a full analysis finally. Okay, so I just keep in your mind the picture of the plus I eigenspaces for JA and how they decompose in this square. Okay, and I'm going to maintain throughout my talk the colors for the A being red and B being green. Okay, so once we have these four half Dirac structures, okay, you can do something interesting. This is something that we developed with Enrique and Gio Cavalcanti, which is called reduction. So it's a way of reducing courant algebroids. You kind of think of them as symplectic manifolds, and you can do a symplectic reduction. So the way that it works is that you have to find reduction data, which in this case, I'll take it to be one of the four half Dirac structures, L plus, let's say. And that will be my reduction data. You could think of that as being like a little Lie algebra that's acting on the space. So we have an injection of L plus into the courant algebroid. It's isotropic. And so if I want to get a reduced courant algebroid, what I should do is take the perpendicular, the co-isotropic, K perp, and then mod out by K. Okay, and then when I do that, that would be fine, but then I need to actually take invariant sections of that bundle to reduce to the quotient. And here, this is where so we have to do something special in this case, which is that L plus, little L plus, that thing is not a Lie algebra that's acting on the base manifold. It's a complex Dirac structure, or a complex half Dirac structure. It's the plus I eigenbundle, right? So it doesn't really act in the usual way on the underlying space. Instead, what it's doing is it's defining a complex structure. So instead of taking K invariants, what it means, what you should do philosophically, is you should take holomorphic sections instead. You should take the kernel of the d-bar operator that you get by letting L plus act by the bracket. And so that's what it means, that little k on the top right. We're supposed to take the coisotropic, modulo the isotropic, and then take invariant sections, which in this case means holomorphic sections. Okay, and so we get a reduced courant algebroid, just like with symplectic reduction. And because we had these four big Dirac structures, all of those four big Dirac structures, they will reduce as well. And I've just explained here the reduction of LA and the reduction of LB. And so we get a pair of Dirac structures in the reduced courant algebroid. What is that kind of structure called? It's exactly a Manin triple. So what we end up with is when we do the reduction with respect to little l plus, we're going to get a holomorphic Manin triple on a complex manifold X plus. And when we do the reduction with respect to little l minus, we're going to get a holomorphic Manin triple with respect to the other complex structure, X minus. Okay, so we get a pair of holomorphic Manin triples. Okay, so this just comes out of this geometry. So, and by the way, I should mention that, so as soon as you see this, you know, what is going on? So you've extracted holomorphic data from this Riemannian structure, okay? And you've extracted quite a lot of it. It's like a pair of complex manifolds now, each of which has all of this holomorphic data. So the natural question is, well, how are they related? How are these two complex manifolds related? The interest, I mean, at first, my first instinct was maybe they're isomorphic, but actually they're not isomorphic. They could be non-isomorphic complex manifolds. And so you start to wonder, what is going on? So we've got holomorphic Manin triples. I colored them red and blue and green with the same coloring in mind. One of them came from JA, the other one came from JB. So what does this mean in terms of the geometry of the underlying space? Whenever you have a Manin triple inside a courant algebroid, you know, those subbundles, these subbundles A and B, right, they have a bracket, they're algebroids, and they project to the tangent of X. And so they give you foliations, the A foliation and the B foliation. So there will be two foliations, or singular foliations, really, on the base manifold, and these would be holomorphic singular foliations. And because A plus B is the whole Courant algebroid, it implies that these two singular foliations are transverse. And so that means that through any point, you're going to have two leaves, one of A, one of B, and they may not, they intersect transversally. They're not necessarily complementary, but the sum of them is the whole space. So you get, I tried to draw it here with a foliation by A leaves and B leaves, and they're transverse, and they intersect in a third foliation. And this foliation is like the intersection of the two algebroids in the Manin triple, and experts will be familiar with the idea that when you take the intersection of two members of a Manin triple, what you get is a Poisson structure. And so this third foliation, which I drew in black, these are the symplectic leaves of a holomorphic Poisson structure. Okay? So we get now all this structure coming for free. Holomorphic Courant algebroids on two complex manifolds, Manin pairs, and holomorphic Poisson structures. Incidentally, these two holomorphic Poisson structures, they had been noticed by Hitchin about 10 years ago, without noticing the Dirac structures, but the Poisson structures, he saw them, he saw that they were there. So the main questions that we have about this reduction are the following. How are the holomorphic Manin triples related? And the second question is, well, okay, fine, all this holomorphic structure, that's great, but what about the metric? The metric is not holomorphic. The metric should be something on top of all this holomorphic structure. So what's the relation with that? Okay, so those are the main questions that I'd like to answer. Okay, any questions about, this is the problem. This is the problem. I could have explained this part 6-7 years ago. Yeah, Mario.
Yeah. What does this minus sign mean when you write A plus, B plus? The word minus, it doesn't mean intersection. What do you mean by that?
You mean the little subscript plus?
Yeah,
minus?
no. If you go to the previous slide. Yeah, you wrote A plus minus B minus. Do you mean?
So here I just mean that because I have two complex structures, I have two complex manifolds, right? X plus and X minus, that's what I call them. X plus is the manifold with the complex structure I plus, and X minus is the one with I minus. And they're the same smooth manifold, okay, fine, but they're different complex structures on that manifold. So as a complex manifold, they're different, and the structure is the same on either one. It's a Manin triple. So I just use plus uniformly to talk about one complex manifold and minus the other.
Yeah, sorry, this wasn't my question.
Oh,
so what do you
sorry.
mean by A plus minus B plus? Does it?
Oh, sorry. This is the intersection of the two Dirac structures. There's a Dirac calculus. You know, when you join the religion of Dirac, right? You start to learn that Dirac structures, you can take the difference, you can take the sum, and you can multiply them by numbers, right? And this is the same thing as taking intersection as Lie algebroids, right?
Okay, thanks.
Yeah. Soon you'll join. Don't worry.
That's right.
Okay. So, but it's just the intersection of the two Lie algebroids, and it corresponds with the intersection of the two foliations. So you can, you know, like any good religion, you can dumb it down at multiple levels. You know, you can go all the way down to the foliation level. Okay. So the question is what.
Can you give an example that we should keep in mind throughout the talk?
An example of the Manin triple. Or GK? One thing you can keep in mind is if you take, let's say that you take, I'll give you a kind of a slightly strange example, but it's a good example. Suppose that you take the manifold to be SU3. This is a real 8-dimensional compact manifold, okay? So a dimension is 8. It has a 3 form, which is the Cartan 3 form on the group, right? And what we can do is we can look at the Lie algebra. Right? The SU3 Lie algebra has a 2-dimensional Cartan, and it has a root system that looks like this. Okay, and then what you could do, so this is the complexification of SU3. I'm drawing a picture of the Cartan, right, with the roots in it, okay? And so what you do is you take the two-dimensional Cartan, let's say R2, which is the real Cartan, and you choose a complex structure on that. And then what you do is you extend it to a complex structure of the Lie algebra by splitting the roots into two sides. That way, when you take an element of this root space and with this root space, if you take the Lie bracket, it will be in this root space, and so it will be closed under the Lie bracket. So this will be a complex structure which is invariant on the Lie algebra, SU3. So you choose an invariant complex structure on the Lie algebra, okay? From that, you can generate the rest of the structure. What you can do is you can left and right translate this complex structure to two complex structures on the compact group, okay? And then you also have the bi-invariant metric. Okay, so all this structure is a bi-Hermitian structure which satisfies the equations of Gates-Hall-Rocek. So the manifold SU3 is a generalized Kahler manifold with three-form flux, and it has all of this structure of these holomorphic foliations and so on. Is that okay? Okay. Okay, now, the first thing that I would like to explain is the case which we call symplectic type. And this is a simplification which made our life very much easier before we could attack the main problem. And what it means is that one of the GC structures, one of the generalized complex structures, we're assuming is symplectic. Okay, so JA is symplectic. JB could be anything. It doesn't have to be complex. It could be some generalized complex structure like some of the ones that were described by Roberto yesterday, like the stable ones or something. And a special thing that occurs in this case, which is kind of clear just because it's symplectic, is that one of the two foliations becomes trivial. There's only one leaf, the whole manifold. And so that means that instead of having three foliations, you would only have one, because you can't intersect with the trivial one. So we simplified to the case where it's only the B foliation which is interesting, not the A foliation. Okay, so one foliation is trivial, and in this case, using the religious Dirac calculus, what you can deduce in just a few lines is that you can determine what the relationship is between the two Poisson structures. So it turns out that the B foliation and the Poisson structure are basically equivalent. And so what you end up seeing is that once A is trivial, the B plus and the B minus, they're really the holomorphic Poisson structures. And the relationship between them is that they're B field equivalent. So that means that when we say that the Poisson structures are B field equivalent, what it means is that the foliation, the symplectic foliations of the two Poisson structures are the same, but the two form on each leaf is changed by adding a closed two form, which is global on the manifold. So you can always do this to a Poisson structure. You can just take a global two form and just add it to all the leaves. And as long as you don't ruin the non-degeneracy on each leaf, then that will still be a Poisson structure. This is called B-field gauge transformations. It was studied by all the people here. Allen, Cervera, Burstein, everyone. Okay, so that's pretty good. So now we know that the Poisson structures, at least in this special case, they are related by a B-field gauge transformation. So that's a hint as to what the relationship should be between the Poisson structures. And now we need the fundamental lemma of the subject, the Burstein shuffle. Does this look familiar? So we begin with a symplectic groupoid, okay? And this symplectic groupoid looks over and sees a B field, a two form, a closed two form, okay? And this B field, it could make use of it. It could use this thing. What is it going to do? Well, one thing it could do is you could use the B field to modify the Poisson tensor. I'm in the real category here. You just apply the B field to the Poisson tensor and you get another Poisson tensor, which is called pi B. Okay? But the other thing that it could do is it could use the target map and pull back this B field and add it to the symplectic form. And it turns out that these operations are beautifully compatible. What happens is that the target map moves over to this new Poisson manifold and remains a Poisson map, as long as you modify the symplectic groupoid form by this T star of B. So if you want to move onto that B field, you need to pull it back on that side, add it to the symplectic form, and what you will get is obviously not going to be a groupoid because it's mapping to two different Poisson manifolds. Instead, what you get is a Morita equivalence between the two Poisson structures. And then you could move the other leg by pulling back by source, and you end up with delta star B, which then is multiplicative, and so this modification then is a groupoid. And it is the symplectic groupoid of the new Poisson tensor. So this is a way of walking around without changing the Morita equivalence class of your Poisson structure. Now, of course, this would be well known to people who have only one true love, which is the cotangent bundle. This is just the magnetic deformation of the cotangent bundle. But nevertheless, it works for symplectic groupoids, and it's a very nice construction that I learned from this paper of Enrique and Olga Radko. Okay, so what we need, because we're in the holomorphic category, is a holomorphic version of the Bernstein shuffle. And so you start with a holomorphic symplectic groupoid and this thing which I called beta. And it's going to use beta, but now it's going to be more extreme. Now this beta is going to deform the holomorphic Poisson manifold. That means that it's not just the Poisson structure that can change, it's also the complex structure that can change. So this is important for our application because we have changing complex structures. So what we need is basically it's a Mohr-Cartan element which deforms this Poisson manifold. Now this Mohr-Cartan element deforms X and sigma, just like I drew here. And the interesting thing is that there's a way of lifting it, this Mohr-Cartan element, to a two form, a B field, which then you can add to the holomorphic symplectic form. So this is slightly different from the real category where it was a two form both below and above. Now what's below is a Mohr-Cartan element, more general. Okay, it could be a B field, but in general it wouldn't be. And then you would lift this and deform this via the target. Okay, and so then we've got a deformation of the groupoid as a principled groupoid bundle. We get a Morita equivalence also in the same Morita equivalence class. And then you can also use the other foot and step over to the new Poisson manifold. Okay, and this is a construction that I used in a couple of papers, one with Mike Bailey and one with Francis Bischoff. Okay, just to say a couple more words about this. Beta is a Mohr-Cartan element which deforms this groupoid, okay? And it does so with a fixed Morita class. So I just wanted to put this up just for fun, that the deformation theory of Poisson manifolds, holomorphic Poisson manifolds, is quite interesting. It's actually, if you want to know how to deform a holomorphic Poisson manifold, it's controlled by the multi-vector fields, the holomorphic multi-vector fields, okay, which is not a surprise. I mean, it's very similar in the real case. But it's interesting that you do need to truncate it. You can't have the zero multi-vector fields. You have to truncate. This is a well-known fact in algebraic geometry for this particular problem. And so here what you see are holomorphic 1 forms, 2 forms, and 3 forms, which I've put the Dolbeault resolution vertically. Okay, and so a Mohr-Cartan element would be in the red 2 spots. It would consist of a Dolbeault 0, 1 form with values in T1, 0. That would deform the complex structure. And then it also would give a holomorphic bivector, and that would deform the Poisson tensor. So these two are necessary. This is for the deformation of the complex structure, and this is for the deformation of the Poisson tensor. And they're jointly closed in the total complex. But there's also a bracket, sorry, I forgot to say, there's the Schouten bracket, and there's a differential, which is differentiation Lie derivative by the Poisson tensor. So we have this very nice deformation theory for the base. But the cool thing is that because we have a Poisson tensor, then we know that there's a natural map from differential forms to multivectors. Okay, and that is a DGLA homomorphism from the forms, because this is the Lie algebroid. So this is the exterior powers of the Lie algebroid now. Okay, it has a differential, it's a bialgebroid, and it has the Koszul bracket. And the map given by the Poisson tensor is a DGLA homomorphism. So that means that there's another deformation problem here, sitting, coming from the Lie algebroid. This is still over the base, I'm still over the manifold X, which maps to the Moore-Cartan problem for deformation of holomorphic Poisson tensors. So what's this? It turns out that this is precisely the deformation theory of the groupoid, staying within its Morita equivalence class. That's what the purpose of this is. And we see that if you deform the groupoid in this Morita equivalence class, then there will be a natural map to this deformation problem, which deforms the base. And so you end up with this very nice picture interpreting what this Poisson tensor is doing in terms of deforming groupoids. And this is very much related to all of the recent literature that was developed by Krynick and his students about groupoid deformations. This is an implementation of this in a very particular case and in the holomorphic category. Yeah.
Since this is what I think on the left side, more like a deformation of the algebra used by the constructor. Because I mean,
You can think of this, it is true that there's an interpretation of this as a deformation of a Dirac structure. That is true. So if you're in the Dirac world, that's what the interpretation would be. But if you're in the world of spaces, you would like to know what is the space that's changing? And the space that's changing is the groupoid.
but isn't there a problem of integration?
Well, yeah, there's always the problem of integration. You know I ignore this problem. For me, they're always integrable. We always integrate. Okay, so what does that mean for the symplectic type case? It means that we are able to take the groupoid of one of the Hitchin-Poisson structures on the X minus side, and we're able to deform it by taking one step and two steps. We're able to deform it to produce the Morita equivalence between the two sides, and then we're also able to produce the groupoid on the other side, or if you wish, you could start here and go the other way, okay? So there's an effective way of producing the holomorphic symplectic Morita equivalence between the two sides. So this is what is the answer to question number one. It's telling us that they're Morita equivalent but not isomorphic as complex manifolds. They are Morita equivalent as holomorphic Poisson manifolds, however. Okay, and we see that we have a Morita equivalence. So that means that hidden in the geometry, hidden in the equations of generalized Kahler, is a class in the Picard group, Picard groupoid, really, morphism space. This is the Picard category defined by Burstein and Weinstein of Morita equivalences up to isomorphism between holomorphic Poisson structures. So this is just a class in the Picard group, and it turns out that this class is the exact analog of the Kahler class of Kahler geometry, which normally would be a class in cohomology, an abelian group. Here it's in a morphism space in a category. It's the Picard category of symplectic Morita equivalences. Okay, and then the second question we answered with Francis and Maxime Zabzin, which is what is the metric in all of this? Okay, you know, it's nice to have this beautiful holomorphic data, but where's the degrees of freedom of the metric? The metric turns out to be a Lagrangian bisection, C infinity Lagrangian bisection of this Morita equivalence. And that's just a remarkable fact. That means that the degree of freedom for this metric is a single scalar function, just like in the Kahler case, where it's a single Kahler potential function, which varies the metric. So this is a very important case where you can study Riemannian geometry. Instead of having a huge number of components of your Riemannian tensor, you just have a single function, which describes the metric as this thing wobbles around inside this holomorphic symplectic Morita equivalence. And then if you want to recover the B field that you use to take that step, you can just take the holomorphic symplectic form, ambient here, and restrict it to that Lagrangian. It's only Lagrangian for the imaginary part, so for the real part, it's not Lagrangian, and we get a 2 form. That 2 form is the Bernstein shuffle 2 form. Okay, so this is the picture that we had a couple of years ago. Any questions about that? So I'm going to go now to the general case. So this is how we solved the problem for symplectic type. The answer was that the holomorphic Poisson structures were Morita equivalent. Okay, in the general case, it will not be the case. The 2 holomorphic Poisson structures, we thought for a while that they were Morita equivalent, but it turns out that they're not. It's a lot more complicated, and that's what I'm going to go.
Hey, Marco, is there like an example I should keep in mind? Chenchang here. For this theory, generalized Kahler, holomorphic Poisson, bursting shift, is there like a typical example I should keep in mind? AMM or what?
So one example you could keep in mind is for the holomorphic step. You could take, for example, if you take, let's say that you have a complex manifold. Okay? You can take the holomorphic cotangent bundle of X, holomorphic cotangent bundle. Okay, that's a complex symplectic manifold. But then you could also assume that we have a Kahler form, omega, Kahler. Okay, if you have a Kahler form, you can pull this back and you can add it to you could take the holomorphic symplectic canonical 2 form on here, and you can add pi upper star of omega. Okay, and something very interesting happens when you do this, because this holomorphic symplectic form is a holomorphic 2-0 form on T star X. But omega is a Kahler form, so it's a 1-1 form. So when you add this to this, it can no longer be holomorphic on T star X. However, you could think of this as being another, but what happens is that this is another, this I could write it as omega prime, right, which is another holomorphic symplectic form, but for a different complex structure on the holomorphic cotangent bundle, which makes it into an affine vector bundle, and it's no longer a vector bundle. So there's a way of deforming this complex manifold and its symplectic structure from the holomorphic cotangent to what they call the twisted holomorphic cotangent. And that is exactly a Bernstein step in the holomorphic category. Okay, so in order to attack the general case, I went to consult my guru, Pavel Cervera. Okay, and I read this paper of his from 2011, which everyone in this room should read, in my opinion. It's only 20 pages long, or even less. Okay, and it's a beautiful paper in which he generalizes the Atiyah-Bott and Alexeyev-Meinrankin-Malkin construction of moduli spaces of flat connections on surfaces. And what he says here is he says that we study moduli spaces of flat connections on surfaces with boundary, where we put boundary conditions given by Lagrangian Lie subalgebras. That's the idea. So the idea is that, okay, if you don't have boundary, Atiyah-Bott tell you that the moduli space of flat connections is symplectic. If you have boundary, then it's Poisson. But if you have boundary and you put a boundary condition, and if the boundary condition is Lagrangian in the appropriate sense, so that would mean that now inside this Lie algebra, which has a invariant inner product, what you want is for this subalgebra H, which decorates this component of the boundary, you want it to be a Lagrangian Lie subalgebra. People who went to the school would be very familiar with this from Anna's talks. You have a Lagrangian Lie subalgebra, and you decorate this edge of the boundary with that Lagrangian Lie subalgebra, and this edge, you could use a different one if you want. You could use the same one for everything if you wanted, but you use a different one as long as the intersection of H1 and H3 is 0. and the intersection of H3 and H2 is 0, and the intersection of H2 and H1 is 0, and so on. So pairwise, if you put a vertex, you need their intersections to be 0. And then the moduli spaces of flat connections on this decorated surface, and what it means is that the parallel transport along this edge has to be in the group that integrates this HI. So it's a reduction of structure on the decorations. That's what's happening. You're changing the moduli space because you're considering certain constrained elements. Anyway, he proves that it's symplectic. A special case that he worked out is he gave a beautiful construction of the Lou-Weinstein double symplectic groupoid of a Manin triple of Lie algebras. So if you have oops, what did I do? Yeah, so if you have a Manin triple of Lie algebras, where the double has the inner product, then what you could do is you could look at the surface being just a square, a filled-in square, with 4 boundaries, 4 vertices, and then you just look at the connections that, when restricted to the top and bottom, lie in A, and on the sides lie in B. And then because they have to be flat, then you know that A1, B1 must be equal to B2, A2. And that submanifold of this thing is the Lou-Weinstein symplectic groupoid. And then by putting these squares together, you can see how the composition works in the groupoid. You can compose top to bottom or side to side. So there's 2 composition laws, and both of them are Lagrangians, meaning that it's a symplectic groupoid in 2 ways. So this is what we want to do. We want to apply the same idea, okay? Because we have now a Manin triple on a manifold. Okay, so we need to make the right moduli spaces. Okay. So in our case, okay, however, everything becomes complex, and this is very annoying. Everything becomes complex Lie algebroids, but you have to press on. And not only that, but if I look at the Lie algebroids that I have, they don't intersect in 0. I have Lagrangian Lie subalgebroids, so I can use these as boundary conditions according to Chavera. But the problem is that they intersect. LA and LB intersect precisely in this thing that gave us the complex structure, right? And so what's the idea? What are you supposed to do, according to this yoga, is that, well, okay, if you do this, that means that you're going to have residual gauge symmetry at these 4 points. That's what it means. So that means that you consider the moduli space of flat connections with reduction of structure, but you're going to be left with residual gauge symmetry given by the action of the holomorphic, anti-holomorphic vector fields for I+. And so what that means is that you should take the holomorphic functions on that space. So there's going to be a complex structure on that space, and you should take the holomorphic functions. So it's like a form of reduction again. It's like an infinite dimensional version of our courant reduction. Okay, so that's the idea, and we implement that. And then we get this nightmare. Okay, tic-tac-toe. Okay, so there are many different possibilities of what you could use to decorate the sides. You could use LA, or you could use LA bar, the complex conjugate. You could use LB, or you could use LB bar. Or you could use LB bar and LB, right? And so I just drew all of the possibilities in a consistent way here. Okay, and the vertices are labeled by the thing that we need to quotient by. So we have 4 labels. These 4 vertex labels are the same, right? The upper right quadrant, the upper left quadrant, and so on. The quadrants, they have the same reduction that we need to do. Okay, but yeah, and the one that's maybe the most difficult is maybe the one in the middle, because it has all 4 boundary conditions at the same time, all different. Okay, and this picture is symmetric under a complex conjugation. It will be a reflection through the origin. That's what complex conjugation does. So that means that we should find all these moduli spaces. That's it. That's the integration. Okay, so I tried to draw a picture of this. Okay, so this is late at night, and you start getting increasingly, you start to wonder if you're going crazy. So I changed the size of the squares. So we have our 9 squares. Okay, And what do we see in the top right? So if we focus on the top right, that's supposed to be this thing. But this is looking a lot like Cervera's example. It's the same on the both sides and on the top and the bottom. And so what you'll get is a double groupoid in that case. So this is a double groupoid. So is this at the bottom right. So there are 4 double groupoids. They come in complex conjugate pairs. So the top right is complex conjugate to the bottom left. Okay, and it's a double groupoid over X plus. This is a double groupoid over X plus, and this is a double groupoid over X plus bar, which I remind you, when you take the complex conjugate of a complex manifold, you get a different complex manifold. It's a completely different complex manifold, not isomorphic to the original. And it's still a complex manifold. It's like taking the coefficients of your polynomial and taking the complex conjugate of it. It defines a new complex manifold. This is like the Galois action. So anyway, we have a double groupoid over X plus, a double groupoid over X minus, and then they're complex conjugates. So if you wish, what you could do is just cut the picture, in half or something, and then just look at 1/2. Okay, but then these 2 double groupoids, the one over X plus and the one over X minus, they are related by this double Morita equivalence. So the side groupoid of D plus is Morita, is not Morita. So this side groupoid, this is a Poisson groupoid. And the red is a Poisson groupoid, and the green is also a Poisson groupoid. And D is a symplectic double groupoid. That's the pattern. So everything that's in blue is symplectic, and everything that's in the Christmas colors, green and red, is Poisson. And then everything in black is just a Manin triple. So there's only 4 things in black: X plus, X minus, and their complex conjugates. So what we see is that the Poisson groupoids, A plus and A minus, on the top right and bottom right, they're not symplectically Morita equivalent, but they're Poisson Morita equivalent. They're related by a Poisson bibundle, ZA. Okay, and then the ZA has an integration, which is the ZD. That's a symplectic groupoid over ZA, but it's also a Morita equivalence between B plus and B minus, the Poisson groupoids of the sides of the D plus and D minus. So anyway, you end up with these Morita equivalences between double symplectic groupoids, this, and then also it goes to the complex conjugate, and it kind of goes around in a circle, and then in the middle you have something that relates everything together, another symplectic Morita double, I don't even know what to call it, double Morita double equivalence, I don't really know. If anyone has a good argument for what it should be called, please let me know. So this is what it is. If you want to write it in the more standard double notation, here there's only one, each space occurs only once in this picture. So you have the 9 symplectic spaces in blue, and you have the red and green Poisson spaces, and then you have the Manin triples on the 4 spaces. So this is the diagram. This is in my opinion, this is the end. It is the integration of the generalized Kahler structure.
Can you say again what is C?
So C is symplectic, first of all, and it is let's just start here, right? So if you start at D plus, this is a symplectic double groupoid relating the side groupoids A plus and B plus. These are Poisson groupoids. Okay, and then the point is that if you want to know, for example, what like if you look at B plus and B minus bar, B plus and B minus bar, they're on 2 different complex manifolds, but they are Poisson Morita equivalent via WB. So WB relates B plus and B minus bar. Okay. All right, and it has an integration, but never mind that. Okay, on the other hand, if I look at the complex conjugate of this entire green line, I get this green line, and the WB bar, that's a Morita equivalence between B minus and B plus bar. Okay, and these are Poisson Morita equivalents. WB and WB bar are Poisson Morita equivalences. And these Poisson Morita equivalences are themselves symplectically Morita equivalent by C. Okay, but C also does the same job for ZA and ZA bar, right? I mean, you could start a religion with this kind of thing. I don't know why it does this. Okay, so that means that we have Burstein dancing even further. So this is something that is very helpful for understanding this complicated gadget. Okay, there's a way of starting at one of these blue points and constructing any of the other blue points, okay, by doing this Burstein shuffle. But see, the funny thing is that because it's a double groupoid, oh, sorry.
Symplectic type, what is simplified?
What is simplified is that the A direction is trivial, so the groupoid integrating A would just be the pair groupoid. So A plus would be pair, A minus would be pair, all of the red stuff would be trivial. That's what would happen in that case. Okay, now it's time is up, or oh, okay. Oh yeah, oh, collapsing. Oh right, okay. I couldn't tell what that motion was. Okay, so right. So the point is that we wanted to have a simple way of constructing this. So by analogy with the symplectic type case, we would like to be able, for example, to construct WD from D plus, or construct D minus bar from D plus. Okay, and the reason that you can do this is because look how many legs the double groupoid has. It has 4 legs. So it's like a 4-legged animal, right? And it can do 4 independent Burstein steps, shuffles, right? So you can use this source to move this way. You could use the target to move this way, or you could use these source and target to move down, or you could use a source from this side and a source from the other side to move one down and one to the left. And in this way, you can populate everything just by doing B-field transforms using these Mohr-Cartan elements, and one by one, and they all commute. So that's what I tried to indicate here. So you can modify D plus using a pair of 2 forms which exist on the side groupoids, A plus and B plus, which you can pull back by the 2 legs that you have on each direction. Okay, and these are B fields coming from Mohr-Cartan elements in the original GK manifold. And in this way, you could construct all the 9 of the double symplectic spaces by doing this Burstein shuffle. Okay, and then finally, the point is that there is also a Lagrangian brane bisection. There's going to be a brane bisection here, here. They will have complex conjugates, and also in here. I don't know the complete set of conditions yet for the brane bisections, but I believe that they're completely determined by a imaginary Lagrangian brane bisection in WD and in ZD, and then they generate the one in C. But I have yet to. We have yet to prove that. So that's what we believe is the picture. And when I say we, I refer to the 2 people who are working with me on this project. We're tired. One of them is Yusong Jiang, who's here. Where is he? Right there. Hi, Yusong, my student. And Danielle Alvarez, who's not present, but he's in Toronto, joining us from Zoom, I hope. Hi, Daniel. It's also based upon the symplectic type work that I did with Francis and Maxime. And it's also related to ongoing work on generalized Kahler geometry that I'm doing with Leonard Doppenschmidt, who's here somewhere. Is he not? Oh dear, oh, another COVID. Okay, and then of course my guru, Pavel, without whose help I wouldn't have been able to figure it out. Thank you for your attention.
Thank you very much, Marco, for your very nice lecture. And so if you have some questions, maybe Enrique has something to say about the boosting style.
Yeah, I was just wondering if in this more general picture, you can now go back and say something about the generalized Kahler potential, as you did for the symplectic case.
Right. So I can't make a super precise statement just because I don't know that last condition yet, but it does seem as if there are two Lagrangian submanifolds, one inside W, one in two of these side holomorphic symplectic Morita thingies, the Z and the W. I believe that there's a smooth imaginary Lagrangian bisection in each one of those, which is multiplicative only in one direction but not the other. And I think that there's freedom of, there's freedom of this kind of function, single scalar function in one direction. And so you end up having 2 degrees of freedom, one on one side and one on the other. There's still a possibility that maybe one side is determined by the other and there really is only one Lagrangian, which is what the physicists kind of seem to be saying, but we can't establish that yet. It really seems at this moment that there are 2 degrees of freedom, just that one of them goes away in the symplectic type case. But I'm not sure. It seems like there's probably a condition that we're missing. So, yeah. But indeed, it hopefully will still be the case that there's a single scalar function which governs this thing.
My turn? Okay. Thank you, Marco, for Thank you, Marco, for the wonderful talk. Thank you.
You're welcome.
I have like a couple of questions. There were like a lot of your combinatoric thing at the end. I see 4 colors. 0, 0, 0, 1, 1, 0, 1, 1. 4 colors. 4 lines between the 4 colors.
You see, the religion
square.
Begins. This is how it starts. Yeah.
Well,
Right.
and the square filling it.
Yes.
And I think it's some sort of double or like say double, some sort of Kahn projection onto this double thingy.
Did you say a Kahn projection?
Yeah.
Okay, we should talk later.
Okay.
I'm not ready for that.
Okay, that's one thing. Like a colored double Kahn projection. I don't know. I just see something. Maybe
Interesting. Very interesting.
Let's talk more.
Yeah.
Second thing, like I would like to like what's a motivating example for generalized Kahler? Generalized Kahler. Is there something you put generalized Kahler structure on top of? Like I don't know. So this AMM groupoid, can you put generalized Kahler?
Yeah,
even?
there are these structures that I just described here. They live on groups. They live also on homogeneous spaces.
Homogeneous spaces.
for
Groups are
groups.
homogeneous.
And they are related, as you can see from the construction of splitting the roots, they are related to the construction of the Poisson Lie group structure. So they are somehow very close to all of the spaces that you see in the AMM story. But I don't really have anything precise to say about the relationship between this picture I described and all of those one-shifted symplectic structures.
Okay.
But yeah, that remains to be done.
So
It's a good question.
So the last thing also, like commenting on Mariu's observation, maybe it's nothing related to it. Like this direct thingy, you have plus minus, right? You have plus minus multiplication. Is it a linear category? Because it's not.
So you're talking about the yoga
Dirac.
of Dirac structures,
Right.
where you can add and multiply them and
Right,
so
right.
on.
Is it even?
Well, they form a nice structure, but the problem is that there's always the requirement of transversality in order for the operations to be well defined. So there's an assumption that the Dirac structures have to be transverse in the
Yeah,
appropriate
let's
way.
ignore that.
If you ignore that, then they form a nice
Linear category. So you mean the morphism? They can also plus minus.
I don't know if you would call it a linear category, but maybe a category in torsors, something like that. Yeah.
It could be a 2-vector space. Put them all together.
More good ideas, yeah, good ideas coming from Chen Chang.
Well, I just have a curiosity about these intriguing pictures that you make in the plane. Are you really thinking about them in the plane, or what's the best way to imagine them, put them together?
Well, I think that Yeah, I think because these are moduli spaces of surfaces, I think it makes sense to draw them in the plane for that reason. I think so. Yeah. I don't have any deeper.
I think it's a related question. Do you have a moduli space theoretic description of the shuffle?
No, but yeah, I want one. Yeah. Yusong, you heard the question, right? Okay.
Yeah. Marco, I have first a comment, which is if you're going to use Enrique's name, you should not call it a shuffle, but a dribble, given his interests.
The dribble?
Yes.
Okay, got it.
And the other thing is, at some point, when you consulted your guru, your guru was talking about moduli spaces of flat connections.
Yeah.
But there is no moduli space of flat connections on your story. So you are using that as an inspiration for integration.
Yes.
There is an assumption too, because it's not true that you always have an integrable. That was I guess, the comment.
Yes. You're right. Yeah.
And so, if it's not integrable, what is going on then?
If it's not integrable, right?
What is the potential, the Kahler
If it's not
potential?
integrable, then I would do, like, for example, in practice, when we used the symplectic type case in order to produce examples of generalized Kahler metrics, because you can use it as a construction mechanism. You build the holomorphic thing, and then you just choose a C-infinity Lagrangian, and it gives you a metric. So it's a way of constructing metrics, actually. And when we do that, all we need is just a local coordinate expression for the Morita equivalent space. So, I mean, if you want, like, from a practical point of view, I just need enough of that Morita equivalence to be able to get a bisection, and then I'm okay.
So you are using local groupoids in...
Yeah.
Okay.
But I mean, you could imagine that, if you're starting now to take that metric and to start flowing it, as we do when we study generalized Kahler-Ricci flow, because that's what's happening, that Lagrangian is undergoing a flow, then you could encounter problems. So there would be, in principle, some relation between integrability and geometric flows, which would be really cool, but we're not there yet.
Okay, thanks.
So thank you so much for the nice lecture. So it's great to see that you have very close to finish this very long project, and I wanted to propose an exercise to you so that you can maybe present in the next Poisson.
Yes.
So I find that there is one missing ingredient in your picture, which is the role of holomorphic divergences. So a holomorphic divergence is a smooth section of the current algebroid, such that via the Dorfman bracket it preserves both L plus and L minus. And we have encountered this in two places. First, if you have a generalized Kahler-Ricci soliton, it determines a holomorphic divergence. And secondly, in my work with Andoni de Arriba and Luis Alvarez Consul, holomorphic divergences play a role in the construction of an n equals to 2 superconformal structure, embedding into the kernel of the RAM.
Interesting.
So I think there should be, your picture should be enlarged to include this holomorphic divergence in some way. And yeah, my exercise is whether you can put this into the picture over the next 2 years.
Good. Yes. I take the challenge.
Okay. Have some work to do.
Yeah.
Okay. So thanks again to the speaker for.
Thanks.
Nice. And we're going for lunch.